So the next talk is by Moritz WALTER. He's a graduate student in the information science at the University of Sheffield, working, as I understand, with Valerie.
Yes, that's correct. Yeah, thank you for the kind introduction. And I also want to thank the organizer for firstly organizing this great event and also giving me the opportunity to speak here and present some of my research. Yeah, if you read my title, so my project is in the area of explainable machine learning. And yeah, therefore I'm very grateful we had this great talk by Pavel yesterday because it laid the groundwork so that you are better prepared to understand my project. And yeah, so my project is attempting to interpret neural network models for toxicity prediction. And the novel aspect is to try to leverage chemical features that have been learned in hidden neurons. So if we think of a traditional neural network or deep neural network with multiple hidden layers and use that for QSUM modeling, so which may be a classification or regression task. So we have an input layer where we do some chemical fingerprint or some molecular descriptor as input, and then we have in these hidden layers kind of intermediate representations of the chemical input that are in the end used to make predictions. And for this to work in the end, these hidden layers need to learn some meaningful representation of the chemicals that are then suitable to make a prediction in the end. So if we think of, for example, about mutagenicity as the toxicity endpoint, then we would expect that these hidden neurons need to learn something about, say, aromatic nitro compounds or polycyclic aromatic hydrocarbons. Because if the model is able to make accurate prediction, it needs to somehow have an understanding, some perception of these kind of structures. And yeah, so the aim is now to find chemical features or structures that are responsible for the activation of individual hidden neurons. We developed a workflow that is able to do that, and it uses different lines of evidence. So we use training compounds that have a strong activation for individual neurons. Then we also come from the input features, which are here bits of Morgan fingerprint, and then these are all connected with a weight to a hidden neuron. And yeah, for each neuron we take a subset of the training set with a strong activation and fingerprint bits that have a high learned weight for this hidden neuron. Then we use a technique called formal concept analysis to find meaningful combinations of compounds and bits that these compounds share in a data set. And then from there we can see what parts of the training compounds are encoding these atom environments, and from that we can look at connected substructures of bits and extract these. And these are then chemical structures that are responsible for activation of a given neuron. So we do that for all the hidden neurons, and then the next step is to use these extracted substructures in a way that we can explain predictions made by the model. For that, I use a technique called integrated gradients. It was also on one of the slides of Pavel's talk yesterday. And it's one of these techniques that are gradient based. So to give you some intuition, what happens if you change a feature, an input feature to some extent, how does that impact on the output of the model? And so before, this technique has only been used on the input layer to get importance for input features for the prediction, but the same technique can equally apply on hidden neurons to figure out which hidden neuron has the highest importance for a given prediction. And so just for this simplified case, if you have 5 neurons in a layer, then for each of these neurons would get an importance score. And so these can be positive or negative, depending on whether they contribute to a positive or negative prediction. And then how do we bring this together with the chemical substructures that we have extracted in the first step? So we have this importance value for each neuron, and then we have for each neuron as chemical substructures that we have extracted in the first step. And what we then do to create a final explanation of a prediction, for each neuron we have these importance values, and then simply share it by all the atoms the substructure matches. So here the first neuron seems to be found here a aromatic nitro structure, and in the second case it seems to be the whole aromatic ring alongside the amine group. It was the match. And if we then aggregate this for all neurons, or in this case it's just these two neurons, then we would get to the result that the nitro group was more relevant to the prediction as opposed to the rest of the molecule. And so Pavel also talked about benchmarking new approaches to existing methods, and I will compare this method to applying integrated gradients on input features. It's one of the established methods, I would say, to interpret these models. And now what's the exact model that I've used for this validation task? So we extracted data for Ames mutagicity from different publicly available sources. And so I've done modeling with the experimental Ames data, but actually the model or the results I will show here are regarding a model that was trained on structural alerts for mutagenicity. I will explain why. So the advantage there is that we have rules that are defined by human, and we exactly know which atoms are responsible for positive label. So as soon as one of the compound matches any of these structural alerts, it will be assigned a positive label, and that's what the model tries to predict. And what's nice about mutagenicity is the fact that we have so many known structural features that are responsible for this kind of toxicity. And so I use the alerts in LASA's direct system as the set of rules. And so I'm here explaining a neural network with 1 hidden layers consisting of 512 neurons, and the input were among fingerprints of radius 1. And so overall this task is not very challenging to the model, so that's why we get here a very good performance on the test set. But as Pavel also said yesterday, if you don't have a good predictive model in the first place, it's very difficult at all to explain the model. And so how do we then eventually evaluate how well we can explain predictions? So one thing is we look at individual compounds, and we use this attribution AUC metric to get a measure of how well, or how good an individual explanation for a compound is. And we also did, we looked at the distribution of all the compounds. And a second thing is what we did is, because some of the structural alerts are way more frequent in the data set than others. And so if you just look at the distribution, that would be very much dominated by the most frequent alerts. So what we also did is we computed the average AUC for each alert, and then looked at the distribution of the average scores we get for individual alerts. But first looking at individual compounds. And so I'm comparing my method, which I call here integrated gradients on hidden neurons, to applying integrated gradients on input. So here, if you focus on the left plot, so these are line plots, which each dot, each part of the line is an individual compound, and they were just for each method sorted in decreasing order. And if you look at this as well as the median AUC from this distribution, so it's just here, like 150th compound, something like that, you can see that the previously published method slightly higher scores, although it seems that both methods give very high scores for a large number of compounds before that, and some compounds where the methods don't give a good explanation. But if you look then at a scatter plot where each dot is an individual compound, and on the x-axis we have the performance on the previous method, and on the y-axis the performance on my method. So we can see there are some dots where we are above the diagonal, where my method seems to perform better, And well, yeah, unfortunately, also a lot of dots where my method seems to be inferior. And yeah, also, of course, you can see there's a high accumulation of dots where both methods seem to give a very good explanation. So what I call now alert performances, so the average AUC scores for individual alerts. Yeah, there we get a bit of a different picture here. Both methods almost have the same score, so we have then almost equal amount of alerts where my method performs better than the previous method, and yeah, equal amount to alerts where the previous method is superior. Just looking at a few exemplary compounds now. So here, aromatic nitro, here the input features method gives a perfect AUC score because the four atoms that are part of the alert have been assigned a higher attribution than all the other atoms. That's what then would lead to a perfect AUC score. Whereas my method, seems to highlight the whole aromatic ring as well as the nitro group, which in the end does not lead to the perfect AUC score, but can still be considered a correct explanation, I would argue. And what I noticed as a rule of thumb with an AUC of around 0.8, we usually have a fairly good explanation. Then a bit of a different example, isocyanate. You must know it's a very rare alert in this data set. So this previous method still comes up with the correct explanation, but that's here my explanation is incorrect here, just the aromatic rings with the nitrogen get highlighted, and this is then like a random assignment and not a good explanation. So I've noticed that in some cases with rare alerts, my method to extract the substructures in the first step fails. And of course, the method in the end is only as good as the substructures I've extracted. And if I don't have the respective substructures, then my method cannot explain these predictions correctly. But then there are other examples where, for some reason, using integrate gradients on input does not quite give the correct answer. And somehow my method correctly identifies the features that seem to be perfectly matching the alerts, so the ground truth that we are trying to achieve. And so a general trend that I notice often, my method is superior on if you have larger alert structures where you have to compose the whole alert. And yet, I guess it kind of makes sense because what we expect is that the hidden layers of a neural network accumulate or put together different input features to form larger features to make predictions. And so there's strengths and limitations of both methods, it seems. And I'm great in time. So to already come to the conclusion, we developed a method to visualize chemical features that are learned in hidden layers. So these are then chemical features that are responsible for activation of certain hidden neurons. And then in the second step, we use these extracted fragments as a novel method to interpret neural network models. But as I said, so this method is, so how well this method can explain prediction is very much limited by the extracted fragments that have been extracted in the first step. And so if we could improve this part of the workflow, I suppose we could get even better model explanations. And so then, how I feel about this whole topic, there are so many model explanation techniques now, and it seems all of them have some strengths and weaknesses, which may depend on which data set we're looking at or even which examples of a data set. And therefore I think there's much more studies required in benchmarking to figure out which should be the best tools that we want to use going forward. And then I come to my acknowledgement slide. So I want to thank LASA Limited for funding my PhD, and my supervisors Walter from Sheffield and Sam from LASA for their great support in this project. And then I want to thank you for your attention, and I'm happy to answer your questions.
Okay, we actually do have time for questions.
Thanks. Very nice work for the interpretation of neural network. Just want to ask a quick question. I noticed you chose Morgan fingerprint radius of 1, and where I see all other common works usually choose 2, 3, 4. So is there any special reason? Is that related to like your extracted fragments in the hidden layers?
Yeah, so the first motivation for that is I tried different radii for the fingerprints, and it seemed that radius 1 gave the best performance. So what I take from this is that radius 1 is sufficient to find all the features that are necessary to solve this task. Of course, if you go to radius 2, you get more information, you have larger environments that are encoded, but at the same time, if you then go to a fixed bit representation, you end up with bit collisions, which kind of may pollute the signal. And yeah, in just, at least for this endpoint mutagenicity, it seemed that radius 1 was sufficient. And if you increase the radius, you just get a slight drop in performance, as I think because of the bit collisions. Yeah, I hope that answers your question.
Thank you for your presentation. It was quite clear, and I would like just to ask if your methodology can be applied for deeper neural networks. Because as I understood, you use only one hidden layer to understand the feature extraction, but if we apply, for example, several layers with a dropout, with different activation functions, we can use integrated gradients there.
Yeah, maybe if I go back to the slide. Yeah, so this vector I have here, directly explicitly uses the connection from the input layer to the first bit layer. And of course, we only have this information for the first bit layer. Yeah, I'm currently still working on extending that to deeper architectures. And the idea would be then, if we have, of course, expected substructures for the first layer, we will use that as input then for the second layer. And then it would generalize to any depth. Yeah, but it's something I'm still looking at. Although, of course, I also noticed for mutagenicity, there's not really any benefit in using deeper architecture because the model seems to be, capturing everything that's necessary. But yeah, of course, that's a very relevant aspect to have a method that generalizes to all these cases. And yeah, I mean, maybe the general idea to look at which chemical features are in the end recognized in hidden neurons may well be also interesting for like graph convolutional neural networks, even though there we may need a different approach to do that. But yeah, I hope this idea is maybe picked up, and at some point this will be a method widely used. Would be great, at least. Yeah, thank you.
Okay, let's close this talk and move to the last presentation of the day. Thank you, Moritz, for the presentation.